You might see the remote. TV. There is. All right. So why don't we get started? Because the first thing we're going to do is just talk about plans and how that went and all of that, which is helpful. But today we're going to talk about temperature, not just one temperature, but temperatures, because there are a couple of different kinds of temperature that are useful for us. Oh, I can't make it go away. But anyway, there's an S behind there. And we're basically almost always going to use something called potential temperature, which is what the temperature variable in the model is, theta. Unless you're looking at observations of temperature, and then you might get a different kind of temperature. But there's some concepts behind what the different temperatures mean that are useful for us to know, and it kind of gets our brain started not talking about latitude and longitude, but talking about how things change with depth in a way that's going to be helpful for us. That makes sense to everybody? Oh. What did we talk about last time? Global budgets. And before that, we talked about estuary budgets. And so the global budgets are all about like the energy, right? The energy coming in from sun and going out is infrared and maybe making it into the ocean if it makes all the way through the clouds and the atmosphere and the exchanges between the atmosphere and the ocean. So what we didn't talk about much was the temperature of the ocean and the temperature of the atmosphere, which is related to, but not exactly the same as energy. So that's what we're going to try and get on today. Is like how to think about temperature in a way that makes that conversion easier than it is in sort of with all the full power of like thermodynamics. And next time, so we've been talking about budgets for scalars, and your paper one is probably scalars. By scalar means something that doesn't have a direction, just like temperature or salinity or pressure or something like that. Next time, we are going to start talking about vectors like momentum. And so that will require us to think about directions and forces and pushing this way and pushing that way and spinning this way and spinning that way. So we're going to spend a lot of time moving through the key ways that the force equations work in the ocean so that we can take observations of things like salinity and temperature and convert them into currents and which way the currents are going. Start to think about the causes of like the wind goes like this and the heating goes like that. Which way does the current go in response? And that'll give us the tools to really understand what's going on inside the model, but also to head towards things that might or might not change under climate. That makes sense? Okay. So number one, questions on the questions or comments on the plan process. So I'm sorry I haven't gotten all of the plans documents back to everyone yet, but I'm going to try and do that all today. So hopefully you'll have them all back with some comments about things to do. And typical comments are kind of the, I was just saying, Adam, like what you folks would come to office hours for. Like, I kind of did this, but I didn't think it was going to work. And so I was looking at this and then I didn't know which data set. And that's exactly what the response to the plans are going to be. The plans are not pass-fail things. Like I can tell if you have thought about it a lot, and that's sort of like a full credit plans. Sometimes if you haven't made a figure and you haven't whatever, then that I may take points off for that. Or definitely if you like haven't actually put the things into the plans that I asked for, like a hypothesis and the title and those kind of things. Like, but you can be totally wrong in every aspect of what you're proposing in the plans and still get a full credit plans. It's not, these are not right or wrong. These are meant to be an opportunity for feedback to avoid you getting into trouble heading toward the paper. And it's meant to stimulate you getting started thinking. For those of you who maybe like I was in college and like to do things on the last night, you will not be able to write these papers on the last night. You might be able to write them, like put the words in, but you need to have the graphs done before you start that process. Making the graphs and writing these short papers is not a one-day process. It's a couple of different days, largely because you just need to like let the ideas gel, and you'll get a bug and you'll be like, oh, I don't know what to do. I'm frustrated. I'll do something else for a while, then come back to it. That's the right way to approach this kind of thing, not like thinking you can do it all in one push. So that's part of the other reason why the plans get you started thinking it now, start getting some of the pieces together. Does that make sense? And that's also the actual research process. You know, those of you who are like grad students working on research, you know, it's just like years and years and years. And you're like, why is there so little progress? But then every now and then you'll notice that you've done a lot since last year. But each day feels pretty slow most of the time. So that's fairly typical for this thing. Okay. What do people think about plants? How many of you thought it was a really easy thing to do? Some nods. How many of you thought it was a really hard thing? Painful. So what would be, what's an example of something that was hard about it? So what kind of figures? Yeah. So not even what data set or which variables, but like just what's the question? How about the people that thought it was easy? Why did it, what was the easy path? You know, what did you start with an idea, or did you start with like, I could generate this figure?
I definitely started with an idea. I guess the reason why it was easy for me is because I didn't think. Okay.
Yeah. So you can go both ways. You could have like, I want to look at, you know, climate change in the North Atlantic. And then you start thinking like, well, what could I actually do with the tools I have? And that scopes it in. Or you could be like, well, in the homework, we made this figure. Could I have made that figure in a different part of the world? Could I have made that figure at a deeper depth? Would that have been, could I have made that figure in some other way, or with some different data set that I could compare to this data set? Like those kind of pieces might be a good starting point to stimulate ideas. And then, you know, in the introduction, you're going to want to motivate why you did this. And you can do that either way. Like you can motivate it like, it's not a chronological thing. It's not like you start out with the ideas in the introduction necessarily, and then move to the figures, and then move to the conclusions. You might actually start somewhere in the middle and be like, oh, I just learned a cool method. I'm going to use that method somehow. What could I use it on? And then you figure out a couple things and maybe a data set, and then you're like, what would be good questions to ask? And then you go backwards and write an introduction that you have figured out something you want to do, and then learn how to make that and try and make it meaningful and add the introduction. So this, you'll have a bunch of chances to do this, and I'll try and give lots of feedback on the plans part, but also you'll get an enormous amount of feedback on your paper. So you will see how things kind of lock into place with practice. Any other questions? How hard did you find it to make a hypothesis? Or what makes for a good hypothesis?
I have a question of what makes good hypothesis. My hypothesis was like, this will impact this, and I didn't say which direction it would impact. Is that still solid?
Will there be a detectable signal? Yes. That's a detectable connection. So that's a hypothesis. The main thing that makes a hypothesis special is that it's actually tested. And there's a whole, well, I'll come back to that in a second. There's another thing called like a broader, like science question, which you might be motivated by big science questions. Like how does climate change affect the ocean? That's not a hypothesis. A hypothesis is, in this data set, I'm going to examine this thing and the effect of climate change will be detectable in this. Like, it's much more narrow and you're kind of always scoping back and forth between those two. Because the hypothesis will actually get addressed in your paper. The science questions are like way bigger than one paper, but the hypothesis itself on its own doesn't seem very interesting. Science question is really interesting, and you're, picking hypotheses that point towards a bigger science question. And your paper should contain both in some way, but your job is to link them. Like that's what the job of the introduction and the job of the conclusions you draw. And when you say like this result is important because that's exactly where you're linking the hypothesis back to the big science questions. So the last thing I'll say about hypotheses before we move on is there's a philosopher of science called Karl Popper, who I think is very interesting and cool. And he spent a lot of time thinking about what makes science different from pseudoscience, like astrology or something like that. And he was like, they are both methods of thinking with disciplinary like standards, but what's different? And the main thing he came up to be different was in pseudoscience, if your theory doesn't seem to explain something, then you broaden the theory to include the something it doesn't explain. And in science, you have the ability to fail to predict something. You can have a falsifiable hypothesis. So you can have a hypothesis and it might be the case that your explanation does not in fact predict the outcome. And that's the key difference between science and non-science. Non-science is also making predictions, but the predictions after the fact are always kind of modified to be like, oh, well, what I really meant was. And it seems like a trivial thing, but actually you watch certain people trying to wrap their heads around things. Little kids are really good at this. Wrap their heads around why something didn't go the way they predicted. And often they will try and convince you that they did really actually predict that if all the factors had been taken into account. That's not what you're doing. All the factors are already in account in the hypothesis, and it's either true or not. You can recalibrate with a new hypothesis adjacent to the old one and ask it again, and maybe get a different answer. But it's that level of precision is what we're trying to develop in these asking these kind of questions. Okay. All right, so other things. So some ideas about thermodynamics. How many of you have taken the class in thermodynamics specifically? Some number. We will talk about things today, some of which are like kind of familiar through thermodynamics, normal coursework, and some which won't be. But some of the pieces I'm going to talk about are going to be like esoteric even for the people who have taken thermodynamics, but it's the big takeaway is we're trying to connect temperature to energy. That's the thing, and maybe the exchanges of energy to differences in temperature. And so that kind of thing is where we're trying to go, because that's really important for understanding the role of the ocean in climate, as we talked about last time, but we're going to get more there this time. A friend of mine introduced this by saying this, the way to think about this is Earth is special and water is special. And a lot of what's special about Earth is the water, which is a nice way to think about it. So one of the big distinctions between the climate of Earth and the climate of all the other planets in our solar system is there's so much water on Earth at the surface. And so it does a lot of things for the climate. And that's part of what we're trying to understand in this class. And so some of the tools we're going to think about are potential temperature in an ideal gas form. We're actually not going to talk about that in exactly that framework, but then potential and conservative temperatures in seawater, and then stratification and low energy density flow, which doesn't make a whole lot of sense, but we'll get to that when we get there. But that's what that's the topics. Okay. So last time we talked about this one. So what is this show? So what's on the x-axis? Latitude, all right. This is the South Pole, that's the North Pole. This is an ocean, something or other. These are ocean things. What are these lines showing? Energy inputs and outputs to the ocean. And we talked a lot about shortwave, which is which? The sun warming the ocean, and long wave, which is infrared going back up. And this is sort of a net long wave, what's coming down minus what's going up, but that. And sensible is really has to do with temperatures. We're going to talk about how that thing is in a minute. And then latent is another thing we want to focus on from a thermodynamics perspective. We're going to try and wrap our heads more around what those two mean. So, and the big answer here is that the net, you add all those up and you get something that's not quite zero latitude by latitude, even though it looks like it might be zero if you summed up all of the latitudes. What does that mean? Why was that important?
Energy flows towards less energetic parts. And there's the highest energy of the equator and goes.
So it has to spread out somehow from where it's the places where you're getting excess are spreading out around the world. So that's energy transport by the oceans. So the currents, the gyres, mixing, all those things, eddies are all contributing to moving that energy around once it's in the ocean. And we're going to think a lot about the direction of it. Okay, so here's a map where that's trying to be estimated. So that's a map of the net, that net energy flux in colors, with red ones being the ocean was warming up and blue ones being the ocean is cooling off. And those little arrows are saying, you know, there's a complex pattern and different amounts of energy flowing in different places because of different currents and part of this system. And this is how it looks when you break it down basin by basin. So integrating kind of side to side there. But a different way to think about it is like this. This is kind of helpful for what we're talking about today. So this is the same data. It's temperature, heat flux, the temperature at 200 meters. Oh, sorry, wind stress, heat flux, temperature at 200 meters, and the mixed layer depth, which is and so red here is the ocean being heated. Blue is the atmosphere being heated, I think, or maybe it's the other way around. But anyway, hard to tell. Oh, no, blue is the ocean being cooled. And then the swirly bits is the wind stress. And then the temperature at 200 meters are these kind of cyan contours. And it's one particular temperature value, which kind of runs through the middle of the Gulf Stream. So that cyan one is showing you where the Gulf Stream is. And then the green parts are this upper mixed layer, the part of the ocean that's mixed vigorously. So what do you see when you're looking over here? What's moving and what's not moving?
Temperature contour is not moving.
Not a whole lot, or you have to watch really careful to see that it's moving. But the heat flux and the winds are moving around. So what do we call variations in heat flux and winds? Yes, that's the weather. And the weather has interesting patterns. Like there's a nice extratropical cyclone that's spinning off. And so these kind of weather patterns are going really fast in comparison to the motion of the ocean temperatures below it. Even though there's lots of heating and cooling, the ocean temperatures are moving slowly. On this side, the movie is sped up enough to see that the Gulf Stream is actually shedding eddies and looks like a turbulent fluid as well. But at this speed, the atmosphere just looks like random force. It doesn't have any structure because it's going so fast. But the point here is both of these fluids are turbulent, but they're on different time scales. The ocean is moving slower, the atmosphere is moving faster. So what did we talk about last time that maybe gives you a hint as to one of the things that makes the ocean slow versus the atmosphere fast? Specific heat capacity. and actually the heat capacity in general. And we're going to come back to that, but basically you get less temperature change in the ocean when it absorbs energy than you get in the atmosphere absorbing the same amount of energy. And so it changes the rate at which things warm up temperature-wise. And the exchange between the atmosphere and the ocean is really about the difference in temperatures. One is warmer than the other, you get an exchange from the warm to cooler. Possibly this go. Okay. So all this, is it just as easy as describing temperature moving around carrying energy? Not really. This is the challenging part we're going to address today, because temperature is not the natural unit of energy. Under adiabatic conditions, that is without changing the energy, you can change the temperature. And under isothermal conditions, same temperature, you can change the energy. So they are not connected to each other. There's other things, other thermodynamic properties that you need to consider to get the energy from the temperature or the temperature from the energy. It's not a one unique relationship between them. And so the energy depends on both the temperature and the pressure, and to a lesser degree, the salinity. So that's the answer. We need to know something about the pressure. There are other thermodynamic conservation principles, not just energy, things like entropy, enthalpy, free energy. It's very messy. Energy tends to transfer from the hotter to the cooler. And so that air-sea exchange tends to go from the hotter to the cooler. And the temperature difference drives the direction of exchange. Okay. Any idea whether this is going to be extremely loud or not at all loud?
The world today is undoubtedly this problem of not being able to talk to scientists because we don't understand science. They can't talk to us because they don't understand anything else aboard here. This problem, I think it was C.P. Snow first raised it, Sir Charles Snow in private life. In his books, Science and Government, and so on. Mind you, I haven't read it. I'm waiting for the play to come. He says quite rightly, he said, it's no good going up to a scientist and saying to him, as you would to anybody else, good morning, how are you, and so on. He just glare at you, or make a rude retort, or something. You have to speak to him in language that he'll understand. I mean, you've got to say something like, H2SO4, Professor. Don't synthesize anything I wouldn't synthesize. And the reciprocal of pi to your good wife. Now this you will understand. Snow says that nobody consider themselves educated who doesn't know at least the basic language of science. I mean, things like Sir Edward Boyle's law, for example. The greater the external pressure, the greater the volume of hot air. The second law of thermodynamics is very important. I was somewhat shocked the other day to discover that my partner not only doesn't know the second law, he doesn't even know the first law of thermodynamics. Going back to first principle very briefly, thermodynamics, of course, is derived from two Greek words, thermos, meaning hot, you don't drop it, dynamics, meaning dynamic work. And thermodynamics is simply the science of heat and work and the relationships between the two, as laid down in the laws of thermodynamics, which may be expressed in the following simple terms. After the first law of thermodynamics: heat is work and work is heat. Heat is work and work is heat. Very good. The second law of thermodynamics: heat cannot of itself pass from one body to a hotter body. Heat cannot of itself pass from one body to a hotter body. Heat won't pass from a cooler to a hotter. Heat won't pass from a cooler to a hotter. You can try it if you like, but you far better not. You can try it if you like, but you far better not. Cause the cold in the cooler will get hotter as a ruler. The cold in the cooler will get hotter as a ruler. Because the hotter body's heat will pass to the cooler. Because the hotter body's heat will pass to the cooler. Heat is work and work is heat and work is heat and heat is work. Heat will pass by conduction and heat will
we talked about.
Heat will pass by convection.
Convection.
Heat will pass by radiation. And that's a physical law. Heat is work and work's a
All right,
curse.
Chris.
All the heat in the universe.
But anyway, these guys are very funny, but this is I hope you will always remember what the first and second laws of thermodynamics are. The first law, heat is work and work is heat, and the second law, heat can't pass from the cooler to the hot. Right? So that's it. All right. So we put up this complicated set of equations last time being the equations for fluids. There are 9 variables and 9 equations. This one is heat is work plus external. This one is entropy, which comes from this. And this governing equation tells you that entropy means that you transfer from the cooler to the hot, essentially, because that temperature is downstairs. Or the other way around, hotter to the cooler. Okay? So those are the equations we're talking about. Those are the essence of where we're, that's the underlying pieces. It looks very complicated this way. This is the energy of a fluid parcel as it's moving around. And what does this big TDT mean? We talked about that one. Material derivative. So this is the rate of change in time following a fluid parcel is what this guy is. And then it's experiencing other stuff. But this equation is pretty complicated. There's this weird work part as well as the internal energy part. And then there's like temperatures kind of lurking because the energy itself is related to the entropy, and then the entropy is related to the temperature, like a big complicated mess of things. So let's step back a little bit, think a little bit more about heat capacity and energy as it relates to heat capacity without the pressure change part for a little bit. The water has lots of properties that are intertwined with Earth's system and life on Earth. It's the only substance in gas, liquid, and solid form on Earth. Well, obviously without our intervention, but water has an enormous heat capacity. It varies in density. So the oceans are stratified by density, light stuff at the top, dense stuff at the bottom. Most pressure variations in the ocean is hydrostatic. We're going to talk specifically about the hydrostatic balance in detail on next time. But the simple way to remember hydrostatic pressure is the pressure is the weight of everything on top of you. So the more ocean water on top of you, the more pressure you have. The more atmosphere you have on top of you, the more pressure you have. And so we go down to surface level and we have how much pressure? 1 atmosphere of pressure. An interesting choice of units. How much is it? Well, it's the amount of 1 atmosphere above you gives you in pressure, which is 10 decibars or 1 bar. And then when you go down in the ocean, every meter we get another decibar of pressure. So every 10 meters of the ocean gives us another atmosphere of pressure. So they go up very quickly. Okay? And so seawater's heat capacity, equation of state, and chemistry are all related. What it is that makes the water so special is that a little water molecule looks like a Mickey Mouse. Well, these aren't drawn Mickey Mouse. The ears are the hydrogens and the face is the oxygen. And the way the electrons orbit around this, the electrons are more strongly pulled to the oxygen than to the hydrogens. And so the hydrogen is a little bit more positive tendency than the oxygen. And so it tends to get attracted to the neighboring oxygen, which is hooked to hydrogens, which tend to get attracted to the neighboring oxygen. So these dashed lines, those bonds are not as strong as the bonds between the hydrogens and oxygens within each molecule, but it's enough that the molecules cling. And that clinging is what makes for big heat capacity. So the high heat capacity and high latent heat is it takes an awful lot of energy to pull water molecules apart. If they're frozen, to turn them into a liquid takes a lot. If they're in a liquid, to pull them apart and make them a gas takes a lot. To add temperature, make them wiggle versus each other essentially, takes a lot of energy. So all of those are related to this hydrogen bonding aspect. And seawater also differs from pure water by its colligative properties, which is you've got salt and other stuff in there. So the freezing temperature of seawater is about -2 C, not 0. And the boiling temperature is also depressed a little bit. Okay, and also light and sound penetrate in a way. It's affected by this. This is sort of a cool factoid, which I just threw in. So we talked about those SOFAR and RAFOS floats, the acoustically sensed ones. When they put the SOFAR floats down, for the first time, they found out that if they were at a certain depth, they could hear them really far away because the sound waves, if they were headed down, would get bent back because the sound speed is, let's see, it's minimum here. So it speeds up and it kind of gets bent back, or it speeds up and kind of gets bent back into that low sound zone. And so the low sound zone acts like you're talking through a big tube. It's like keeps all the energy of the sound together and doesn't let it spread out. So oceanographers found out about this when they invented these SOFAR floats and put them down to that depth, and we're like, oh my God, you can hear these from really far away. Whales know about this. They can sing all the way across the oceans to their members of their pod. And then actually I think it's World War II or the early part of the Cold War, actually, the Navy figured this out before the SOFAR floats were invented, because they were down there in submarines and they figured out you don't ever ride your submarine around because everybody in the ocean can hear you if you're in that layer. You want to be below or above. You don't want to get there because it's like shouting to the audience around you where you are. And this is related to the variations in temperature and pressure and density. This thermocline, the part where it changes very quickly, is coincident with this SOFAR layer. Okay, sensible heating. Sensible heating is heat that you can sense. That is energy that changes the temperature, can be sensed with a thermometer. Heat, sensible, that's what it is, okay? Sensible heating, we talked about this last time, is a heat capacity times a change in temperature, or a specific heat capacity times a mass times a change in temperature. So we just said that the specific heat capacity of water is about double that of water vapor, 4 times that of ice, 4 times of dry air, different. Well, what about masses? Which one is more massive, like per unit volume? Which is the least massive? Water vapor, water, ice, per unit volume, so density. Water vapor, okay, which is the second? Ice, which is very weird about water, but that's why it floats, right? It's less dense. And then water is more dense. That's even more true of seawater, because ice is also pure water. It rejects the brine when it freezes. And so seawater is not only denser because water is denser than ice, but it's denser because it's salty and more dense. So it's not salty is making it dense, and it's also more dense than ice anyway. Okay, so here's different values, like, so 1 calorie per gram per degree C is the amount for water. That's the specific heat capacity. You can remember it because that's how it's defined. It is actually 1 calorie is the amount of energy it takes to heat 1 gram of water 1 degree C. That's the definition of a calorie. But we often want to use, it doesn't have on this side, we often want to use joules, which convert to watts. And so there's a conversion factor of about 4.8 to get between calories and joules. And I'll put that on another slide. So water vapor and ice are about half that in terms of their specific heat capacity, and air is about 1/4 of that. So if you take the same mass of water and exchange energy with air, the air's temperature is going to change 4 times as much as the water's temperature change as they come into equilibrium. So if you take 10 degrees C air, 0 degrees C water, put them together, you do not end up at 5 degrees C. Okay? You end up at about 2 degrees C, because the air changes its temperature 4 times as much as the water does in order to come into equilibrium. Okay. So here's a little bit more extensive version of that formula, which is just writing out all the units. So a calorie per second, the degree C per second is a calorie per second times this heat capacity, the mass and the specific heat capacity. There's the 1 calorie, so calories, and that was sorry, this divided. Calories cancel, grams cancel, degrees C cancel, and seconds are left over. So that's all you is, that's the relationship. The rate of change of temperature is the input of energy per second times this the heat factor. And if you want to convert calories per second into watts, you first convert calories into joules, and then joules per second is a watt. Okay. All right. Latent heat. When you melt ice, there's an additional melting before you get from 0-degree ice to 0-degree water. There's an extra 80 calories per gram. It's called the latent heat of fusion. So warm ice up to the melting point, then it takes up another 80 calories per gram. Then it becomes liquid water and it starts heating again. So latent heating, sensible heating precedes and comes after the latent heating that changes the phase. Okay. And I'll show a figure in a second that makes this more. There's also a latent heat associated with vaporization and evaporation. That's 540 calories per gram. So a really big number. It takes an awful lot of energy to take 100 degrees C water and turn it into 100 degrees C water vapor. So often this latent heat is the biggest of the forms of heat that's kind of moving around in the Earth system. Water vapor going one way, liquid water coming the other way, implies a whole lot of heat is being transferred in that process. So if you like, you can think of latent heating as the heat that comes out of the closet. It's not detectable until it is there. And this is what you mean is if you're adding energy for a while, if you start with cold ice at -40, you get warmer, the temperature goes up, and then you go into latent heating, melting the ice. Then you start warming again, adding more energy until you get to the boiling point. And then you have to go boop, 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 all the way over here before you start coming up as water vapor again. And these slopes are different. Why are the slopes different? Specific heat capacity. So this is only half a calorie per gram per degree C, and this is 1 calorie per gram per degree C. So that slope should be a factor 2 steeper than this one. Okay. So this is a nice way to think about changing around and jumping around. When you add energy, how does your temperature change at fixed pressure?
Why does it have different heat capacities again?
Just because the bonds between liquids and solids and gases are different. And in water, it turns out that the strongest bonds are in the liquid form. They're a little bit weaker in the solid form, and they're a little bit weaker in the gas, but a lot weaker in the gas form. But in heat capacity units, it's kind of a factor of 2 different. Okay. So this movie is more excessive. Okay, this is the fast one. So this is this observations of surface temperatures on land and in the ocean as the seasons go by, and that's the year and time. This is -25 to 45. This is -2 to 35. So this bright yellow isn't quite as hot as the bright yellow over here, and this blue is only at the freezing point, which isn't as cold as this blue here. So what do you notice about this? The ocean doesn't change as much. So there is this sort of wobbling, the summer temperatures are warmer, but it's not as dramatic as going all the way up and all the way back. The land temperatures are basically following the sun season by season. So but the oceans don't kind of always have the hottest water close to the equator. It doesn't go all the way up to where the sun is brightest in that season. And then even on top of that, the range of temperatures is smaller because the color bars are different. So what happens then if you say you're here in the US as the seasons change? What's the air sea temperature difference in summertime? I could do it for us too, but it's pointing to California first.
Not bad.
Summertime, the land will be hotter than the ocean. And what about in winter? The ocean will be hot. And so the exchange of energy storm by storm that we saw is also going to be season by season. So there are land sea breezes that are driven by that. And there are also monsoons in some parts of the world that are driven by that. It's just because the land heats up faster than the ocean heats up. And that happens over the course of a day and over the course of a season, and also under climate change. On all of those, the land heats up more than the ocean does. And why is that? Heat capacity. And it's not only the specific heat capacity, which for land is a little bit lower than it is for water, but actually more of the water is involved in the heating because it's mixing over and over through that mixed layer at the surface. So it's not just the surface skin layer that warms up, it's like the upper 100 meters or so that has to warm up. Whereas in land, it's like centimeters that warms up, maybe meters. Okay. So what then does latent heating look like? Okay, this is not how this works to look at this. All right, so this is sea ice, or this is a reconstruction of sea ice. And so this little wiggle is showing how the sea ice is evolving as observed by satellites. Ticking up in days, so they're kind of modest changes. And there's sort of redistribution of the sea ice, like we can't see the individual flows and things at this level, but stuff's moving around. It's kind of mushy in some places. It's more solid packed ice in other places, and it's kind of getting pushed around with the seasons. When we speed up the movie to now be ticking by in months instead of in days, you can see that it's got kind of a jittery form. And now the colors here indicate age. So the whitest ones are the oldest multi-year ice that's frozen year after year after year, and so it's thick. And the thin stuff comes and goes every year. It's seasonal ice. And so you can see that there are all kinds of interactions where the seasonal ice gets kicked out, or even sometimes the multi-year ice gets kicked out. And then, but you know, in the traditional steady state, the multi-year ice over here, kind of against the Canadian coastline, would be growing back at the same rate as any ice was being lost out the side. But as we get into the 90s, maybe I should fast forward a bit, and into the 2000s, into the later 2000s, into the 2010s, what's happening? There's less old ice, and not only that, but now there's even open water during the summer. So the Arctic is one of the fastest changing places in the world in terms of climate change. And the ice, that latent heat that it takes to melt the ice, is part of the energy budget you think about when you think about the Arctic changes. So it's not only that the ice has to be warm to the melting point, you also need to add the latent heat of fusion in order to melt it. Okay. What about the moisture part? This is just a cool video which shows satellite observations of water vapor during an El Nino. And then it's animated and colored for very intense. I think it's colored maybe for precipitation. That's probably right. And it's just kind of cool. You can see the storms. You can see all this equatorial stuff. So why is there so much moisture at the equator?
More evaporation.
More evaporation. Why is there more evaporation? Because there's more energy. The energy is warming the ocean. It's releasing. It's overcoming that latent heat of vaporization, and it's coming up, and then it's getting transported along with these storms from the equator toward the poles, both hemispheres. What does that do to the energy? It redistributes it, right? there's water vapor going this way and then raining and then coming back and getting evaporated again. So the exchange of water vapor towards the poles and liquid water towards the equator is basically an energy transfer in terms of the latent heat of vaporization. That makes sense? And so about a third of the energy rebalancing that's needed by the Earth system is in this. A third is in atmospheric sensible temperatures, and a third is in ocean sensible heats. Okay.
What did you just say that the third that this is showing comes from the heat of vaporization?
Yeah. So it's the latent heat of vaporization, because even if that water vapor is at the same temperature going back and forth, the fact that it's vapor systematically heading poleward and liquid water systematically heading southward, that you're sending 540 calories per gram every time you send water vapor and bring back liquid water. And so this deficit, deficit excess budget we talked about before requires this amount of energy transport. These dashed lines are showing the combination of the atmospheric sensible and latent. And then this one, these poleward transports are by the ocean, are the ocean sensible. Really three parts, that energy budget. Okay, so that's the end of our story about meridional heat transport. What about vertical heat transport, or vertical just like temperature variations? So this is what temperature looks like in the atmosphere. The troposphere, the tropopause, the stratosphere, the stratopause, the mesosphere, and the thermosphere. And there's different explanations for each of these, which we'll come back to in a second. And then the ocean has the mixed layer at the top, and then a thermocline, and then a cold, deep, and bottom waters. Most of the water in the ocean is in the bottom waters. The second biggest is the deep waters, then the thermocline waters, and then the mixed layer. So most of the ocean is actually just kind of close to 2 degrees C. And that's interesting to think about, and we'll come back to the reason for that as we go on, but that's something to keep in mind. So what happens if I take some of this water down here and bring it up to the surface in terms of temperature? Also allows me to clean my keyboard.
Looks warm.
Does it get warmer or does it get colder? So if I'm cleaning my keyboard, I have compressed gas or compressed air in there, and then colder. Yeah. So the expansion doing what? Allowing it to get cold. So we have expansion, cooling, contraction, heating. So it's like it's like an air conditioner running or a refrigerator running. Every time you go up, there's less weight of stuff on top of you, so your pressure is going down. So you're expanding. Every time you go down, you're compressing. And there's an energy. You don't even have to exchange energy, but you're definitely going to change your temperature. Okay. And the same is true here. The troposphere and the tropopause is where all this vigorous convection is happening. So clouds are going from, at least in the tropics, are going from the surface all the way up to make these big anvils, and they're taller than Mount Everest, to school, whatever. There's all kinds of cool stuff. And you see these on a nice clear day. They're these big clouds that are going all the way up to the top of the troposphere. But look at the temperature in the troposphere. It goes from 300 down to about 220. But there's a lot of vertical mixing going on. What's happening? If you start at 300 and you go up to 220, your pressure drops by a factor of 10. So you're expanding an awful lot. So this, in some important sense, this stuff over here and this stuff over here are at the same temperature. Because going up and down is changing your temperature. It's not the same temperature that you have if you measure it with a thermometer, but it's the same temperature you would potentially have if you brought those air masses together at the same pressure. So that's the meaning of potential temperature. It is the temperature you potentially have when you account for the pressure effects. Okay? So if we reference the potential temperature to the surface pressure, 1,000 millibars, 1 bar, 1 atmosphere, we could bring this colder air down and it would do what? Getting compressed, compressed, compressed. It's getting hotter or getting colder? Hotter. How much hotter is it going to get? Well, it's going to get 80 degrees hotter. And that is exactly what you need to arrive at the same properties when you get to the surface. And if you take this stuff down here and you move it up there, it's expanding, it's going to get colder. And if this is well mixed vertically, it does not have a uniform temperature, it has a uniform potential temperature. Okay? It's not quite the same in the ocean because the mixed part, it's true of that, but the mixed part is only about 100 meters deep. So even though that's a fair amount of pressure, liquids don't compress as much. So there's actually not a big change in the temperature difference over that first 100 meters in the mixed layer. But if you move water from the deep ocean up to the surface, it would make a big difference. Let me show you what that means in a second. Okay, so we use this. This was one example, but of only part of this. This is close to an adiabatic expansion. Spraying this guy and cleaning up my keyboard. So it's more or less conserving energy as it comes out, but it's changing its volume. Okay. This is a Carnot cycle, which is the most efficient way to do something like a refrigerator or an air conditioner. And there's a cycle where you add energy and staying at the same temperature, you expand as you're adding energy. Then not having any energy come out, you expand some more, but conserving energy. Then you start compressing and it's releasing energy. And then you can compress a little bit more without any energy change. And that cycle, you go do around and around and around, adding energy and taking out energy. Or this is the way it is in an air conditioner. Here's the condenser outside. Here's the evaporator inside. You condense outside and the energy comes out and heats the hot outside. Then it goes around and then you let it evaporate and expand in your house. And then it's cold, takes up energy as it's expanding. Then it goes back and it releases energy. And it takes up energy and it releases energy, it takes up energy. That's how an air conditioner works. That's how the Carnot cycle works. That's how the atmospheric expansion and contraction almost works. Okay, everybody, yeah?
To the last slide,
Mhm.
when it's expanding, the ocean is expanding near the top. It should be colder than the bottom, right? But it's not.
It's not the only thing. So the key thing that I mentioned here was look at these clouds. That means there's a lot of vertical mixing. Maybe there's not any vertical mixing in the ocean. Maybe it's highly stratified on top of the expansion and contraction piece. That's why we need to be a little bit more careful before we get there. And so here's a profile of exactly that kind of thinking. Here is a temperature-based profile, and here is a potential temperature-based profile. Here is the density based on temperature, and here is the density based on potential temperature. And the sigma units just means subtract 1,000 off. Just oceanographers get tired of writing 1-0 before they get to the interesting bit. So this is going around in the kind of 20s. So it's 1,020 for the real density. Okay. So if you just didn't have any expansion, and it looks like it's warmer down here than it is up there. And it is actually warmer in terms of what a thermometer would measure. But if you raise it up to here, what does it do? It expands. And so it'll get cool, just like that. And then you push it down, it'll get hotter because it'll be compressed. And so this profile might be sort of like a vertical mixing profile, might not. We can't really tell because temperature is hard to understand because of this compression and expansion part. But potential temperature, we haven't looked at the equations for yet, but it has the idea that if you expand and contract, it doesn't change, right? This is reference to some particular location where if you bring them all to one spot and then compare them, kind of removing the pressure part, that's the profile you get. Now look, it looks like this is pretty uniform. So it could be vertically mixed or it could just be uniform source, but it wouldn't be hard to mix down here because there's not a lot of change in temperature. There's not a lot of change in density. But now look at all this. So the temperature is getting hot, hot, hot as we go up. And this is only the beginning of the thermocline. That's only at 1,000 meters depth. Doesn't even, surface will be much warmer still. So what happens if you take this little piece of potential temperature and move it up here? And just remember, you don't need to worry about the expansion and contraction, but you might conserve your temperature because you're not getting heated or cooled. What do you find yourself like when you're up here at, say, 2,500 meters? I'm at half a degree. And the neighbors are what? They're much warmer. So what happens? You're denser because you're colder. You fall back down. So in stratification, not stratification of in situ temperature, which is hard to think about, but in stratification of potential temperature, or really in stratification of potential density, the rate of change of potential density tells you whether you are stably stratified, that is light stuff on top of dense stuff, or unstably stratified, light stuff underneath dense stuff, or neutral, same potential density up and down, however you go. And so it takes energy to lift something. So, all right, let me stop. Are there questions about that? Yes.
Is there like a standardized reference for like what we are measuring? Is it always like versus sea level or at one atmosphere or something?
Here are some choices. You could do the surface, and that's called sigma theta, which is that one. You could do 1,000 decibars, 1,000 meters depth. You could do 2,000 decibars, 2,000 meters depth. You could do 4,000. And you kind of want a local one because the weird nonlinearities of the seawater equation of state start to act up at the bottom. And so local ones help disambiguate that. But most of the time you can think about a surface one or maybe the 1,000 meter one.
Maybe we're getting there, but in a situation like in an upwelling zone or something where you do make it past the thing on top.
How do you do it?
Do you like super cool? I mean, that's like a bad word.
No, so this is the next piece I was gonna go to. So, all right. Here is a hunk of water down here. Let's take a cubic meter of water down here. And let's say this one is at 27, whatever. Let's just call it 27.8. And then we're gonna exchange it with one that's up here at 27.7. So I've got a cubic meter of water, that's 1,000, 27.8 kilograms per cubic meter. And I'm gonna exchange it with one that's at 1,027.7 kilograms per cubic meter. And I'm gonna lift it in the process. How far? That far. 1,500 meters. 1,500 meters. Okay. Which one's heavier? I have 1 meter cubed. 1 meter. It's not meant to be that complicated.
The bottom
The bottom one is heavier because it's got more density. How much heavier is it? 0.1 kilograms, 100 grams. And I need to carry 100 grams up 1,500 meters. And at the same time, push down something that's buoyant and then exchange it. How much potential energy have I changed? A lot, right? I moved 100 grams up 1,500 meters, which is the same amount, well, my conversion. But there's energy involved because we're basically taking things that are heavy and lifting them up. So in that case, in upwelling, which we're going to talk about in a couple weeks, the wind is providing energy that's lifting the dense stuff up to the surface. And it's just continually lifting against this kind of a mass gradient and just pulling the heavy stuff up. And maybe it's mixing it up, or maybe it's just lifting it and displacing the lighter stuff out of the way. But there is if you turn off the wind, the upwelling stops and it falls back down because it wants to go down because it has light stuff sitting right next to heavy stuff. And it would rather be light stuff on top of heavy stuff in terms of releasing its potential energy. So the only reason that it can hold on to that potential energy and be sort of stationary is because the wind is continually pushing it up. It would like to fall back. That makes sense? Okay, so takes energy to lift up. It also, we talked about transporting energy from equator to poles. It turns out that potential temperature is also a natural way to do that. Doesn't matter what depth you're at, you can convert it into an exchange of energy at the surface because it's referenced to zero pressure. So very naturally, if you take the surface specific heat capacity, the surface density, and the potential temperature and the velocity horizontally, this product gives you the horizontal transport of energy. So those horizontal exchanges of energy are best framed in terms of transfers of potential temperature, not real temperature. Okay. All right. Back to that. Talk about it more. Okay. One more concept. So here's that idea of raising a water mass out of its environment. So we take something that's got a density at some lower layer and we lift it up here. And what does it find? Well, it compares its density here. Potential density doesn't change, but you want to compare it to the potential density at a different level. So here's the ambient, this tilde is the ambient potential density versus the potential density that this guy finds itself at. But the potential density doesn't change when you lift it because it's expanding and doing all the things where the potential temperature is supposed to. So what's the relationship between this guy and this guy to make it go back down? It gets up there and it finds itself as what density compared to the ambient density is going to want to go back down. More dense will tend to sink back down. And the same thing, if you took something and pushed it down, it would find itself less dense, it would want to pop back up. So if this background, the density is decreasing as you go up, sorry, this is a weird science convention. The rate of change of this background potential density with Z is negative, then you are stable. And if it is positive, it would be unstable. That would be where you lift yourself up and you find yourself lighter than the environment and you keep going. Okay?
Are you comparing the two potential densities, or are you displacing a potential density and then comparing the densities that they both turn out to be where they are?
So if you had put the reference level right there, it wouldn't matter because they'd be the same. But the potential density part is allowing you not to worry about that. The potential density is the one that takes care of the expansion and compression aspects.
Oh, so you look at
Potential
so you're
density.
looking at potential density.
So you're always looking at potential density versus your neighboring potential densities. And if you happen to be at your reference level, it would also be equal to the densities. Okay. So this little guy, the Brunt Weissela or buoyancy frequency, N, is just proportional to this derivative with a negative sign and then some factors out front that makes it a frequency. This frequency is the frequency that it would oscillate. If you pushed it down and popped back up, it would bounce up and down on this frequency. And that, when we get to internal waves at the end, this frequency is really important because one kind of wave you could have, just like the waves at the surface of the ocean, are an interior density layer bouncing up and down, trying to level itself back up. And then if it was going straight up and down, it would have this frequency. Okay, so once again, stare at this. Think about it. All right. Okay, so a couple of equations that back all this up, which is more just to kind of get see what a little bit what it's like, but until you go to actually calculate one of these, you probably don't need to remember too much. What is the equation of state like? Well, the density, this is the linear equation of state, which isn't that accurate. It's missing a lot of these pieces that we've been talking about, but it's a simple thing to think is the density is like some background value minus a coefficient times temperature versus reference to temperature. So when the temperature goes up, what happens to the density? Goes down, because it's negative slope, right? Negative coefficient there. Opposite with salinity, there's another coefficient, it's a plus sign now. So when the salinity goes up, the density goes up. And pressure, when the pressure goes up, the density also goes up. So all of those are corrected. If we did this for a potential density, we would kind of have factored out this guy. And there would be different ones for salinity and for temperature, but the pressure compressibility would be factored out. Okay. You can rewrite our thermodynamic equations using all of this in a lot of really weird ways. So you can come up with the Gibbs function, the specific enthalpy, the specific internal energy, the specific entropy, all these different things. And so all of those thermodynamic equations can be transformed from one into the other into the other. And they're all kind of complicated. But we can use potential temperature to simplify our lives. So let me have it in the next slide. Yes. The potential temperature equation is really easy. It's just potential temperature is conserved up, down, left, right, following the fluid, unless you're heating. At which point you can gain potential temperature. So that's an easy thing to think about. There's a T downstairs here, which is the real temperature, because potential temperature is actually an entropy, not a temperature, which is super hard and complicated to think about, except it doesn't really matter. You can change the potential temperature by heating it or cooling it, but otherwise it's conserved. So we really need to think. Okay. And there's a more complicated thing called the conservative temperature, which our potential temperature, our idea was that it would be an adiabatic relocation going from the bottom up. So adding no or taking away no energy. It's actually not that accurate because if you mix, you do kind of rearrange the energy in seawater. So there's like a more accurate thing you can do, which is that you are paying attention to the potential enthalpy, not the potential energy. And whatever, they're not that different. There's a more accurate one, which actually even ECHO doesn't use, but we know that it's true of seawater, called the conservative temperature. And people are trying to get us to switch over. Along with this potential temperature equation, there's a potential density equation, which looks almost the same way. It's just the potential density is conserved following motion of a particle, even if it's going up and down, unless you change it. And how do you change it? Well, you change it by heating, or you change it by adding salt. Okay. All right. This is a slightly more complicated version of the equation of state. So now you can still see there's a temperature bit and there's a salinity bit, but now there's a weird temperature squared bit, and then there's a pressure in here modifying the temperature bit. And then this one is still not the real one. The real one has 72 terms in this, and they're all tuned to experimental verification. So seawater is not like an ideal gas at all. It's ridiculously complicated in analytic form. So we don't actually do this very often. We just download a toolbox for MATLAB or Python that just calculates the potential density or the potential temperature from the temperature that you have and the salinity you have and the pressure you have. And so remember, this is the key form. We're getting down to the potential density, the potential temperature, or this doesn't have change in heating and cooling, but are mostly conserved. And then this is a decent approximation based on, this is the one for. This is a decent approximation from the ones before, from the formulas before. If you do this for, if you did this for ideal gas law, you also could write potential temperature as just a function of the temperature and the pressure. They link together a little more simply because ideal gases are simpler than water. And then here are all the crazy coefficients. All right, so all of that is in there if you want to. So let's step back and just think about what all this means for a second before we go. This is 2 layers of an ocean model. That I ran a long time ago, but it's still a nice example. Oops. Keep clicking on those. Okay. If the potential density and the potential temperature are conserved following the motion of the fluid, once you're away from the surface and you're not getting heated or cooled anymore, you can just watch it go. Like the water will just carry around its potential temperature, its potential density with it. So you can make an ocean model, which is just stacked layers at different potential densities, from the surface density all the way down to the density at the bottom. This is such a model. This is just showing 2 of the layers. The thickness of the layer is shaded here. And then you can tell which sense they're moving. So, and then this little purple line is basically where that density contacts the surface. So there's some kind of cooling going on here, which is creating this water. And then it's riding along that density as it gets deeper and thinner. And then it loops over and comes back up here. And then it's disappearing as it heats up. So it's losing energy in the atmosphere, gaining energy in the atmosphere. This is 1 layer denser, which contacts the surface a little bit closer to the pole. Why is that? Colder. The cold and dense and pole and warm and less dense at the equator. So the denser water will go farther. You have to go farther north before it gets to touch the surface. But it also has a similar pattern. And so you can imagine all these eddies and interesting things happening as these layers are kind of wobbling around on top of each other and exchanging densities with the atmosphere that allows them to switch from one layer to the next. They go to a lighter layer if they're getting warm, then they go to a heavier layer if they're getting cool. That makes sense?
Is this a slice?
This is looking from above. So this is west, that's north. And it's like an idealized ocean basin. It's kind of like an Atlantic. It's about the same dimensions as the Atlantic. But this is starting to imagine like the way that the water flows as it comes down and disconnects from the surface. Now it's going to conserve its density and slide along in a layer that has varying thickness. When it gets thinner, it has to speed up. When it gets thicker, it can slow down just like pipe flow. And those thicknesses differ, all those pieces differ. And as you get denser, you get closer and closer to the pole. Okay, last question before we go. If it gets denser as you go to the pole, where is all of that extremely dense bottom water from? Most of the ocean is filled with this extremely dense bottom or deep water. Where does it touch the surface? Can't touch at the equator, right? That's really light. And in the mid latitudes, we see that the density is increasing more and more as we go toward the pole. So where does it touch? What's true about the surface properties where you're making that extremely dense water? What would you want this to happen at the surface? You'd want the salinity to increase. You want to make it super dense.
Okay.
And you want it to be really, really cold. So you can imagine that it was so cold that it would like flash freeze the surface, go to the freezing point and then just drop, but gain a lot of salinity because you're pulling all the fresh water out to leave sea ice behind. Turns out that only happens in 2 places in the world, the Ross and Weddell Sea around Antarctica. And so most of the ocean is filled with water from these tiny marginal seas around Antarctica. Because that water is so dense, once it drops, it just goes underneath everything else. The second most dense waters come from the North Atlantic, kind of around Greenland, where you have the same kind of conditions. You're forming sea ice. The water is actually really salty in the Atlantic because the Mediterranean as well. And it falls. It actually turns out to be a little saltier than the Antarctic conditions, but it's not quite as dense, doesn't get quite as cold, and it comes in kind of on top of it. So those water masses are what makes up the vast majority of the oceans are from these few places. So in fact, the surface expression versus the volume that they occupy, the surface area, they're inverse. So the more area you represent at the surface of the ocean, the less volume you occupy in the ocean, which is super weird. So it's because everything is like complicated. We'll get better at visualizing that. But, okay. All right. Lots of complicated things here. You want to see this from the side? We can look at the side. This one is even weirder. Okay, so this is looking from the side. These are density layers, and then this is the mixed layer, this little blue one. And so this is at 5 north, 30 north, and 55 north. And we're looking, this is the east, and that's the west. So those layers are getting crunched up where they're all bunched together, but then they start to spread out. If those density levels are full, and then they really spread out when the density levels are farther north. All right. Okay, anything else? Any other question? All right, I'll give you comments back on the plans very soon. Papers are due not this Saturday, next Saturday, and that's the first step. And hopefully you'll have a very clear picture of what you want to do after the comments from the plans come back.